Okay, everybody, welcome to class. Okay, we've got an awesome day with a cool demo that we're going to do, if it works. It's always dangerous to do a demo I haven't tested recently, but I think it'll work. So if you're coming in, make sure you get your homework turned in today, right? We'll have these graded always within a week or so, and we can't turn them back in class because it would take too long to hand them out in person, and we're not allowed to pass around the stack anymore. So that means to pick up your homework, which I really, really suggest you do, you'll need to swing by my office sometime or the office, the TA hours. They can give you homework back then. The reason why you want to pick your homework up is because we don't grade every single problem for correctness. We grade some of them for completion because that's a massive stack to get through, and we grade some for correctness, right? So you might get 10 out of 10 on your homework and feel like, fantastic, I understood everything. But you might have actually missed a concept. We just didn't grade it for correctness. Does that make sense? So I will post the solutions always after class. For example, after class today, I'll get that posted so you can double check how to work through things. But I suggest you pick up your homework and make sure that you worked it correctly because you don't want to learn that you did it wrong when you take the midterm. That's not the time to figure it out. Okay? So our learning objectives for today, we talked about free energy, and we kind of have a feel for it, right? It brings together enthalpy and entropy. We said that it has this theoretical part and this experimental part. So we're going to finish talking about that, and we're going to do some examples, because I think it'll really start to sink in as we do a couple examples. A couple quick notes while I'm thinking about it. Today is the first day that we're going to do clicker questions for points in class. And we're also going to start doing clicker questions for reading. Now, the reading questions are super easy. And I don't expect you to read the book and completely understand everything. They tend to be very simple sort of vocabulary, essentially, questions. So the way that I do that, in this reading quizzes section, I assign them, right? So you'll notice that this quiz on chapter 16, so the reading from chapter 16, it starts in 23 hours. So I've assigned it to start basically the day before class, right? And then it'll be due right before class. So it starts at 12 p.m. the day before, and it ends at 12 p.m. That's noon the day of class. That makes sense? And again, these are simple. Like, for example, what does it mean if a reaction is positive? Is it delta G is positive, reaction proceeds in the same direction, or A and B? It's stuff that if you've been even lightly reading the book or coming to class, these should be a breeze, but they're going to help reinforce stuff we talked about. So we've posted on Canvas the reading schedule that you should roughly be following, and it's going to be something like read the first half of this chapter by this day, the second half by this day. And again, if you don't understand it perfectly, that's okay. What I want you to do is at least see it once. Your eyes should pass over that page at least once before you come to class, because it'll make the stuff we cover in class sink in better. Any questions on reading quizzes? Let's try this first one. If there's any issues, let me know. Again, the first one starts in 23 hours, so tomorrow at noon it will open up, and it will be open all the way until noon on Friday, just before class, basically. Okay? And then, again, on Monday, Wednesday, Friday, that'll be the schedule. Okay, the other learning objectives we've got today is, once we do a couple examples of delta G for real reactions, figuring out thermodynamics of real reactions, we're then going to do something that I think is pretty amazing how well it works. We're going to translate this to electrochemistry, like batteries and things like that, where there's an exchange of electrons. It's remarkable how similar it is. You can almost take it just straight across with just one simple conversion formula, and so we'll be doing that. Okay? While we're at it, we're going to talk about species that are oxidized or reduced using something called standard tables for reduction, right? Standard reduction potential tables, or oxidation potential tables. And then lastly, if we have time, but probably next class, we'll do some examples of electrochemistry where different numbers of electrons are involved, and I'll explain what that means later. Okay, so let's start with this one. We left off last time and we'd introduced this idea of a reaction quotient. So turn to your neighbor and remind them what on earth the reaction quotient was and how do you calculate it. Okay, so if that's our reaction, those are all gases. That's CO2, carbon dioxide turning into carbon monoxide plus oxygen. If that's our reaction, how would you write the reaction quotient for this? Anybody remember? Want to take a stab at this? Alan, what do you think? The reaction quotient, you remember how to do this?
Yeah.
So what would the reaction quotient be here?
The pressure of carbon dioxide squared.
Now, okay, the pressure of carbon dioxide or monoxide? So remember, it's products over reactants. So the product is carbon monoxide, right? So we're going to write the pressure, the partial pressure of carbon monoxide, and that's going to be squared, multiplied by what? The pressure of oxygen. Okay?
And then divided by carbon dioxide.
There you go. Okay? So it's products over reactants. You take the coefficient, and those become exponents. We use partial pressures, and if any of these were a liquid or solid, what do? You just ignore it. In the real world, can you ignore it? Heavens no. But in this class, that's what we're going to do because it's an introduction. Okay? So it says if the reaction quotient is equal to 1, right? If the values, when you plug them in here, if this whole side of the equation equals 1, then the natural log of Q, the natural log of 1 is equal to 0, right? So if we go to our expression here, right? This whole second term would go to 0. If it's equal to 1 for Q, this whole term goes to 0, okay? Everybody with me? And remember that this delta RG, that's the change for the reaction in the Gibbs free energy, right? That's equal to this theoretical component, delta RG naught. And again, the naught, unfortunately, does not mean at room temperature like it does with the formation energies. That's the convention they use. What it means is the theoretical part, right? You figured it out as a function of whatever temperature it's happening at, and then this takes into account the experimental component. Any questions on that? I want that to be really clear. Crystal clear? Okay, so let's do an example. Let's start with this reaction. You've got NaHCO3 as a solid, turning into NaOH as a solid, and CO2 as a gas, okay? So for this one, I've given you some information. I've given you delta G for these bottom two, delta GF naught. Again, that means the change in the Gibbs free energy to form that individual compound, and then naught means at steady, standard state conditions, room temperature, 1 atmosphere, okay? So I've given you delta G of formations for those two, but for this one, I've not given you that. For that one, I've given you delta H of formation and the molar entropy, okay? So the question I'm going to ask you first is figure out delta RG naught for this reaction, right? Now, how do we normally figure out delta RG naught? Well, you would just take these individual values, you'd do products minus reactants. The problem here is that I haven't given you the delta G naught of formation. Instead, I've given you delta HF naught and the entropy, the molar entropy, right? So the first thing you're going to have to do to approach a problem like this, what would we do this first time? Anybody think they have an idea? I haven't given you one of the key things you need to know. You need delta G, and I've given you delta H and S. What can we do? How did you calculate free energy? Gibbs free energy equals, yeah.
Gibbs free energy equals H minus TF.
Bingo, right? If you've got these two, you can calculate delta G. You have to know the temperature you're doing it at, right? We're going to assume this is happening at 300 Kelvin, which is basically room temperature, okay? So let's do that first. The very first thing we're going to do is calculate delta G. F means formation. I'm just going to write NaHCO3 so it's clear which one we're doing it for, and then naught. That's going to be equal to, like you said, that's going to be delta H, naught, formation, minus T, S naught, okay? So let's plug those in. That's going to be equal to negative 950.8 kilojoules per mole minus 300 Kelvin multiplied by 102 joules. Careful, that's a joule, whereas the other one's in kilojoules, okay? So let's just convert that to kilojoules right now and say that it's 0.102 kilojoules, okay, per Kelvin per mole. Notice the Kelvin there, that lets our temperature Kelvin cancel out. So punch that in and somebody tell me what you get. I get negative 981.4. Anybody else getting that same thing? Because, good question, the reason I know it's Kelvin is because these delta G naught Fs, the naught for those means that it's at 300 Kelvin. Well, 298 Kelvin, I guess, is room temperature, but it's pretty close, right? That's room temperature, okay? Yeah. I didn't make the rules, yeah. Unfortunately, that's the case. Delta, the delta GF, the formation value, naught, means room temperature. But what she just asked, this one, the delta RG naught does not necessarily mean room temperature. So I apologize. I didn't make that convention. That is what most of the thermodynamic books use, though, for the convention. Okay? So to make it clear, you could also write as a subscript the temperature that this is happening at. If this is happening at 900 Kelvin, you can always put 900 Kelvin underneath that to make it very clear. Okay? Are there any questions on how we weren't given the delta G naught for NaHCO3, but we calculated it using this H minus TS? Is that clear? Yeah, question?
So the question about that is asking for the final partial pressure. So why are we...
Yeah, we'll get to that in a minute. There's basically a couple steps here. To get to the final partial pressure, what do we need to do? We need to go from, if we're wanting to get to the final partial pressure, we're going to have to go from Q to that partial pressure, right? Well, how do we get Q? To get Q, we needed to know this thing and set this equal to 0. So we're figuring this part out still. It's sort of a multi-step problem. I'm walking you through it. Make sense? So now that we know delta G naught F for NaHCO3, go ahead and calculate this. Remember, that's equal to the sum of the products minus the sum of the reactants. And don't forget to multiply it by the number of the coefficient in front of it, the number of moles of each. So go ahead and do that. I think that's our first clicker question today. Okay, that's not the first clicker question, but we're going to use it in a moment. Oh, yeah, that is. So once you get your answer, you're going to get a positive or a negative answer. Go ahead and answer this question. Yeah.
So we're adding together, we're subtracting those.
So you add together the two products, and you make sure to multiply them. Like in this case, it's 1 mole of each, so we don't have to multiply by any number. We just add together NaOH and CO2, and then we're going to subtract from that NaHCO3.
And the numbers we're using are the delta GF naught.
Yep. That's going to be for NaHCO3, and the other two are given in the problem. Yeah. The join code, good question. Okay, that's right there. Text 4554 plus your response to that phone number if you're texting in. Yeah. If you're texting in, that's the phone number up there at the very top of the screen. 315-636-0905. That's the number you text to. Yeah. Oh, yeah, just drop that in. Okay, are people getting an answer? Are people done? Can I wrap this up? Okay, I'm going to close this poll. I see 10-ish people left. Get your answers in. Okay, we're going to close the poll. Okay, people think what? Will it be spontaneous? So, yeah, most people are correct here. You got a positive number. When you do this calculation, you should have gotten a positive number. I think I got, 207? Okay, 207. Because it's a positive number, that means that from your starting state, the reaction happens, your final state had to go up in energy. So is that ever going to be spontaneous? No, that will not. You'd have to drive that reaction with work or some other thing would have to go in to make that happen. It would not happen spontaneously. Okay? So now the next question, I used different values, right, from when I made this, I think, so I'm going to have you modify it. I used this negative 851 for our NaHCO3 last time. But with these values, you get something slightly different. We're getting, negative 981. So for this next step, use the following value for delta Rg naught. I think you need to use 77.2 kilojoules per mole in order to get the answer that I'm going to use, right? So that's my fault for programming this wrong. I used two different sets of answers. So for this next step, assume that the delta Rg naught that you just calculated is actually 77.2 kilojoules per mole. And then we're going to answer the question that this guy asked before, which is, okay, you start this reaction out in a chamber that has excess carbon dioxide. So there's carbon dioxide to start with. It says the reaction will reach equilibrium when delta Rg equals 0. Think about what that means. Delta Rg means the reaction, as you start from reactants and go towards products, there's no change in free energy, right? That means there's no reason for it to continue forward or backwards. Therefore, it's at equilibrium. So this is an important concept. You'll probably want to write it down. Equilibrium occurs when delta Rg is equal to 0. Okay? When delta Rg equals 0. So right here, this is the delta Rg we're talking about. When the change of the Gibbs free energy for the reaction is 0, there's no change, we're going to set this side of it equal to 0. We're going to use the 77.2 kilojoules per mole that we just solved for, right? I guess last class correctly, delta Rg naught. And then we're going to do plus RT natural log Q, and we're going to solve for this, okay? Now in our expression, if you notice the equation we're doing this for, it's a solid turning into a solid plus a gas, which means the only thing in our reaction quotient we care about is going to be our reaction quotient Q in this case. For this guy here, our Q will just be equal to the partial pressure of CO2. Right? Everybody see it? So with that information, go ahead and solve for what the final partial pressure will be. And again, remember to use 77.2 kilojoules per mole, because I think that's what I built the top hat solution around. Okay? Yeah.
Are we to assume 300 Kelvin?
You can assume 300 Kelvin, yeah. And the gas constant, for those that need the reminder, R, the gas constant, is equal to 8.3144 joules per mole Kelvin. Okay? So go ahead and solve for that. make sure you're careful with the kilojoules and joules, that you don't confuse those. So last class, that's the value that we used, and I think that's what I used for the clicker. So there's different thermodynamic tables listed for these things, and last class and the one I used for this problem were slightly different. So if you want to get the right answer, use that 77.2 kilojoules per mole. Because when we calculated it today, we got like 200. So if you used a different value from a different table, it might be off a little bit. In this case, it was off quite a bit. And so to get the right answer, you need to use the 77.2. And if you're stuck, just raise your hand and TA and I can give you a hand. Okay, so the key equation we're going to use is delta Rg equals delta Rg naught plus RT natural log Q. So, and then at equilibrium, you know that this is set to equal to 0.
Okay.
And then you know this, that's your 77.2. You know the gas constant, you know temperature, you just got to solve for Q.
Yeah, I just don't know.
Oh, okay, so isolate natural log Q, get everything on the other side, and then raise both sides e to that number, and that will make the natural log go away. Question? Yeah, to solve for Q when it's inside that natural log, get the natural log Q alone on one side, get everything else on the other side, and then raise e to those both sides of the equation, and the natural log disappears. Yeah, because Q in this case is equal to partial pressure of CO2. Yeah.
Are you setting Rg naught to 0?
Delta Rg is equal to 0. Because delta Rg naught, remember, like, what we care about is the overall reaction, which is both theory and experiment. And if the overall reaction is in equilibrium, it's got to be equal to 0. So delta Rg naught is not 0. I don't know. People that are finishing, are you getting an answer that's one of the options? I haven't made a math error. You're getting one of these two answers. It's possible I broke this, and in that case, everyone will get credit, but go ahead, punch your answer in, and we'll talk about it. We'll solve it together. Sorry, what's that?
You have to use 298.
Oh, and then you get it.
Yeah.
So if you want to get the answer that's up here, you have to use 298 Kelvin, a student noticed, which is the technical room temperature. I say 300, but that's sloppy. It's 298 point something. Okay, so get your answers in another minute or two. We're going to wrap this one up. Okay, I'm going to go ahead and close the poll. Get your final answers in. Okay. Everyone good? Going to close the poll. Okay. Okay, good. So 85% of people think that it is at 2.9 e to the negative 14. We just about solved it. Some people were asking for a reminder. Once you get to this point, right, you know that 0 is equal to this plus that term. How do you actually get to Q? So quick reminder, we're going to bring everything onto one side of the equation. So we're going to put, it's going to be minus 77.2 kilojoules per mole. And you can put that into joules if you want, I guess. 77,200 joules per mole. And then we're going to divide that by that term right there. So that's going to be divided by 8.3144 times 298. That's going to equal natural log of Q. And if you take e to both sides of that equation, the natural log disappears, right? So e to this number gives us that, some 2.9 e to the negative 14. People not getting that, or is that okay? Yeah, question? Oh, good question. So I'm subtracting this over. That made this negative, right? And now you've got this equals that. But if we take e to both sides, it won't get rid of the natural log of q yet. So you have to isolate natural log of q. And the way we do that is dividing both sides by that 8.3144 times 298. Good question. Yeah, Alex? It's the same. Yeah, so I might have actually rounded off slightly different, but it's the same thing. Same gas constant. Yeah. Question, Jari? So, good question. What should the units of Q be? So it's a partial pressure, and the way that we defined a partial pressure was up here, right here. A partial pressure is a molar fraction times the total pressure, right? So it's going to be some fraction of whatever the total pressure was, right? So if that was out of 1 ATM, right, and you get like 0.2, then you have 0.2 ATMs. Okay, good question. Other questions about this? Yeah.
So the equation that you showed.
Okay.
Keep going. Yeah, with that 77.2 plus 8, 3.
Yep.
What equation is that?
So that equation is this right here. That's delta RG, our change in Gibbs free energy, is equal to the theoretical component, delta RG naught, plus the experimental component, RT times natural log Q, where this is the gas constant times temperature.
Now, is that just for this question, or is that...
Oh, this is a generic equation. You will use this over and over on this next homework. Yeah. So this you can always apply. Now, something unique to this question is we said at equilibrium, and that let us set this term to 0. That's not always the case. I might just as easily have given you the partial pressure and said, is it going to proceed forwards or backwards? You plug in this, you plug in that, you figure out if that's positive or negative, and now you know if it's forward or backwards. Question?
So I follow what we're doing, and I get the equations and everything, but can you just kind of explain exactly like what it is we're doing? Like I don't really understand. Like I understand like this is what you plug in here, this is what you do, but I still don't like.
Yeah, physically what this all means. So let me say this. In this case, we started out with 2 solids and a gas, right? So if we actually were to look at like our reaction vessel, right? Let's like draw like the reaction where this is taking place. We said that there was initially some NaHCO3, NaOH, and CO2, right? So you had 2 different solids, right? And some CO2 present, right? This is going to react, right? It's either going to proceed forwards or backwards, right? And our reaction was NaHCO3 reacting to form NaOH plus CO2. Oops. Right? We don't know, right, if it's going to go forward or backwards until we do this full calculation. But once we do that calculation, we know that it's going to either produce more CO2 gas or consume some CO2 gas. And at the end, what we'll be able to do is we're going to be able to tell us exactly what the partial pressure of CO2 is, which is useful, right? It tells you whether this reaction went forward or backwards and what's the final partial pressure, right? The partial pressure, let's say that this hole inside that reaction chamber, it's at 1 atmosphere. Like this room is at 1 atmosphere. The pressure in this room, well, we're high in the mountains, so we're a little less. But it's around 1 atmosphere, right? So right now, the content of the gas in this room is just air. It's 78% nitrogen, 21% oxygen. But if this was a chemical reaction taking place, right, then you might care about figuring out what your final reaction is. Like when it reaches equilibrium, what will be the final partial pressure in this room, right? That's what this is talking about. This tells us, partial pressure may not be the thing you care about, but the thing that you will definitely care about is whether a reaction happens or not. Because we wrote this for some obscure thing that maybe you don't care about. But that could just as easily be whether or not a fire starts, right? Whether something will combust or whether it's going to be fire retardant, meaning like if you try and burn like a polymer, asbestos, that's why they made buildings out of it in the 50s, it was really good at not burning because when you try and oxidize it, the free energy says, oh, you step up in energy, and so that's not favorable. It's those sort of things that we're figuring out how to calculate with this approach. Great question, though. Another question?
Yeah, so with our Q equation of the partial pressures,
Yep.
Is there a certain, so like which one goes on top? Is it the products or the reactants?
Products over reactants. So when we're calculating it for the delta GR naught, then it's the sum of the products minus the sum of the reactants. And when we're calculating the reaction quotient, it's products over reactants. Okay? Great questions. Yeah. I forgot your name. Abigail? The way that you'll know is when you... So in this case, we started out with pure CO2. We said it started out with excess CO2. And we just did the calculation and found out that when it's done, that's the partial pressure of CO2. Is that a big number or a small number? Very small. Basically, we consumed all the CO2 gas, or in other words, the reaction did what? Did it go forward or backwards? It went backwards. It created product. Or in other words, we could have rewritten this reaction and said that's really the one that happens. It forms NaHCO3 because that's the one from a Gibbs energy standpoint that's more favorable. Make sense? Should we do another example? Let's do some more. Okay. So first off, I've done lots and lots and lots of examples on YouTube of these things, so I've got links to them right here. If you don't want to follow links from the course notes, another great place to find them, let me exit out of this. A great place to find them is on top. If you scroll to the very bottom, there's a series of things called worked example problems videos, and I've got them broken up by chapter. So since we're in chapter 16, if I click this, in chapter 16, where'd it go? Oh, up here. Chapter 16, sure enough, you'll find embedded YouTube videos for all sorts of things, right? For doing electrochemistry, here's an example where I work through it in all of its gory detail. Or other ones for Gibbs free energy, you can see them down here. So there's lots more worked out here, okay? That said, maybe let me talk about corrosion. Let me start talking about corrosion, and then on Friday, we will do just examples all day Friday, okay? So chapter 16 picks up here. You don't have to read all of chapter 16. You only need to read the following three sections, 16.1, 16.2, and 16.10. It's got a lot on rates of corrosion that we just didn't have time to get to, so you don't have to read it if you don't want. It's interesting. You don't have to read it, though, okay? And there is a mistake in the book, at least in the third edition. Equation 16.7 should be written like this. It has a slight error in the book. Not many errors in the book, but there is one. Okay? All right, I started out this class saying that Gibbs free energy is related to electrochemistry. We've got a sweet demo for that. So Danny's going to start working on this while I explain it. So what we've got here is pennies. What are pennies made out of? Yeah, it's not copper. If it was before 1982, it was mostly copper. Even then, they started to add the alloys to some things through it. And finally, we wised up and said, if you make this purely out of copper, it's worth more than a penny is worth, right, in terms of copper, and that's stupid, right? So in 1982, they wised up and said, let's make it out of zinc, which is cheap, right, and then just put a foil of copper around it. So the pennies that you use today are zinc coated in copper, okay? So the question, or what we're going to do with these things is we're going to make them react with one another. You've got pennies that definitely I didn't deface one side of, so you can see that it's zinc on one side and copper on the other. Can you see that? Should use a document camera. Yeah. Anyways, we scraped off the copper. We didn't scrape off the copper on one side. Somebody else did, right? And we're going to take these things. So now you've got a copper and zinc stuck to one another, right? And you've probably experienced that maybe, hopefully somebody's told you at some point that you don't like weld dissimilar metals together. You don't put different, like if you got like a steel bolt, you wouldn't put like a different type of a brass nut on it, for example, because it will corrode. So we are going to introduce why, the fundamentals of why it corrodes. And while we're doing that, Danny's going to build a device for us. She's going to take these things and stack them on aluminum foil, okay? And then in between each layer, she's going to take a little bit of vinegar on these pieces of filter paper and stack them. And she's going to stack, I don't know, 6 or 7 or 8 of those things. And be careful that the filter papers don't touch or that will short it out. And then we'll see what it can do in a minute. So while she's doing that, let's explain electrochemistry. Electrochemistry looks like this. Let's say you've got, you can do this at home. If you had a bar of zinc, right, and some other metal on the other side, in this case they're using platinum, right? So there's a platinum coil, and this is a slightly acidic solution. If you connect these two things with a wire, and critically, you put a salt bridge across here, what you will see is that it will spontaneously corrode, okay? In this case, you're going to get zinc dissolving to form zinc 2+. Now, for zinc to turn into zinc 2+, it has to surrender 2 electrons, right? You have to strip off 2 electrons to form the zinc 2+ ion. And zinc 2+, that's soluble. There's some of that in the water that you drink, right? There's tons of dissolved minerals in the water that we drink, especially here in Utah, because we drink runoff, basically, okay? So this is now dissolved. This is a metal, not dissolved, okay? That means that these 2 electrons that basically had to come off of the zinc in order for this thing to dissolve, where did they go? They travel through the wire, right, through some sort of multimeter so you can measure the voltage. They come down over here on this platinum electrode, and then they find, in this acidic solution, they find these H+ ions, right? An acid is just a solution that has lots of H+ ions in it, right? And some of those electrons are going to react with those hydrogen pluses to form H2 gas. So if you created this thing, you would literally see bubbles coming off of this platinum electrode over here. It would be bubbling, and this thing over time would be disappearing. It would be corroding until it disappeared. And this happens completely spontaneously, which is pretty amazing, okay? So it's not just, platinum and zinc you can do this with. Any metal that's dissimilar will have a similar reaction. Now the question is, how do you know which one's going to corrode and which one will be oxidized and which one will be reduced? Yeah, Alex? So great question. Okay, if you didn't have the salt bridge, and the very first time I taught this class, I did this. I was so excited. I had my demo, and it didn't do anything. I didn't look like an idiot. But now I know why you have to have this, right? If you pull this out, what will happen? As electrons travel this way, they're going to build up an excess of negative charge over here and a positive charge over here. So basically you build a battery, right? It's going to stop the flow of future electrons because once you build up an electric field across this thing, the future electrons that would like to travel over here are resisted by the electric field that builds up. So by putting a salt bridge in here that has both positive and negative ions, ideally, salt, sodium chloride works great for this, as long as salt can travel up and through this to basically as negative electrons travel that way, positive cations travel this way, then you don't build up an electric field. So corrosion can continue to happen. This is one of the main reasons why you have to be really careful about salt causing corrosion to happen. Like the whole nightmare of owning a car in Utah is that we salt our roads in the winter to melt the ice for reasons that we will talk about soon, right? But adding all that salt means that there's tons of salt bridge available, right? And so it makes it really easy for corrosion to take place. Now, while she's doing that, let me show you the example of what's happening here. Right? Let's say you've got copper and zinc. This is literally copper and zinc that they put together. You can see that the zinc, it had to start out with some sort of zinc ions in solution, and this is our copper, right? When you put these two things together, this one started to dissolve away, and this one had all the zinc that was in solution start to plate out on it, right? And you've seen this before. You've seen so this is not the same thing as like your bathtub faucet. If you ever seen like the white stuff building up on your bathtub faucet, that is not the same type of corrosion. That's probably just precipitation, meaning all the dissolved solids in our water, the calcium deposits, right, in our water, are just coming out of solution when they find a nice surface and they're nucleating on it. That's different than electrochemical corrosion, okay? Because because it doesn't involve the exchange of electrons. Electrochemistry has to be driven by the exchange of electrons, okay? So consider these two examples. If you've got iron and copper set up in these beakers like that, iron and copper, then the iron gets dissolved and copper gets precipitated. Or in other words, iron gets oxidized because it gains oxidation is loss. It loses electrons to become iron 2+, whereas copper gains electrons, so copper 2+ ions become copper metal. Now you take iron and zinc instead of iron and copper, and it's the exact opposite. Now iron precipitates, meaning it's going to grow, and zinc will dissolve. So what's happening? How come iron can be two totally different things depending on what the other metal is? It has to do with free energy, right? And there's a super handy table that we can use to figure out which one's going to happen. What metal's going to get dissolved and corroded, and which one isn't. So here you've got what's called the standard reduction potential table. So here you've got a whole bunch of reduction reactions. How do we know they're reductions? Because in each case, it's a metal gaining electrons, right? Zinc 2+ adding 2 electrons to form zinc metal, okay? And you've got lots and lots of these different things possible. And what you see on the right over here is the standard electrode potential. A potential is a voltage, right? And you'll notice that at the bottom, these are negative numbers, negative almost 3 volts. And at the top, they're positive numbers, okay? The positive versus negative number tells you whether it's spontaneous or not, okay? Now there's a catch. Does it work?
Yeah, but I wanted the red one.
And it doesn't? It might be just toast. So we're going to kill the lights real quick and check this out. Oh gosh. Some combination of these switches will do what I want it to do. Okay, I'm going to turn this power off for 1 second. Okay. I don't know if you'll be able to see this, but try and see if you can see the color here. You need a light? Okay. Okay, here comes, she's going to touch it with an LED. And only one way works. Does it lighten up? Yeah. Okay. So do you see that color?
My fingers are too big.
Hold that thought. Okay.
Okay.
Anybody see that?
Really light.
Maybe up front you can see that? Okay. Thank you so much, Danny. It needs more voltage. You probably need to add more stacks to make it work. Okay. The red one works? Okay. Come play with this afterwards if you want to see it. I have to wake up the projectors. Okay.
We have to do red.
All right, real quick. Let's see red. How do I do this again? Hey, you guys see that? The red? Yeah? Okay. Thank you. Awesome work, Danny. Okay, so think about all we did here. The only thing that I didn't do anything, first off. The only thing Danny did is we took pennies that some monster defaced, right? And we stacked them up and put a salt bridge between them. Now, we had to stack a bunch. How many did you stack? So she stacked 8 of those together. Now, let's figure out, hypothetically, theoretically, what should the voltage be? We're going to do that using this table, okay? So let's pull up copper and zinc. Let's do this example, okay? So first off, if you have copper and zinc, let's make some assumptions. Let's start out assuming that it's going to be copper 2+, picking up 2 electrons to form copper. And for zinc, it's going to be zinc 2+, picking up 2 electrons to form zinc metal, okay? So those are our 2 reactions. But right now, the way that they're written is 2 reduction reactions. Now, what must every redox reaction have? A reduction and an oxidation. So, what's the problem? What are we going to have to do? One of these is going to have to get flipped. Now, which one is the question? Which one do you flip? Does zinc dissolve into zinc ions? Or does copper? And how do you know? The way that you know is by switching it, and switching it causes the voltage to get switched, right? Instead of negative 0.763, it would become positive 0.763, okay? When that happens, then you can add the 2 together. When you add them together, if you get a positive number, it's spontaneous. You didn't hear wrong. It's opposite of free energy. That's the biggest, terrible, I don't know why they defined it this way. It's opposite of free energy. Again, I didn't do this. Don't look at me with your judging eyes. I didn't define this. A positive voltage is spontaneous. A negative voltage means it requires that voltage for it to happen. Okay? So write that down. The opposite of free energy. A negative free energy is spontaneous. A negative voltage here is not spontaneous. Yeah?
So in terms of which reduction to flip, it's always going to be the smallest number, meaning the most negative?
It'll be the more negative one. Yeah, right? If we flip this one, because it's 0.76, the copper is only, what, 0.3. So when we flip this one, we get a large number, what, around positive 4 or something, right? If you flipped it the wrong way, you get a negative number. And so that tells you, oh, I did it wrong. It'll be the negative 0.4. So just switch it. That makes sense? So let's write this out. So let's write out copper 2 plus, picking up 2 electrons to yield copper metal. That has, I'm going to call it V naught. That's equal to, what's up here? 0.34. 0.34 volts. Meanwhile, zinc 2 plus with 2 electrons gives us zinc, and it has a voltage of negative 0.763, I think. Negative 0.763, okay? Well, first off, if we add those together, we're already lost because we have 2 reductions, and so that's a problem. So you have to flip one of them, and the one that you flip is the more negative. The more negative one, in this case zinc, gets flipped, and that way when you, let's flip it and write out what it is. When we flip it, now we've got zinc yielding zinc 2 plus 2 electrons. That gives us a reduction potential, now it's an oxidation potential, of positive 0.763. Oh yeah, I added these together wrong. Right, so that now goes away. Now you can add these 2 reactions, just add them up, so sum them up, and the reaction becomes copper 2 plus zinc gives us zinc 2 plus copper. Okay? The electrons cancel out. In this case, the electrons cancel out. They won't always. And now we can write delta V naught equals, what is that? Math. 0.34 plus 0.763. Oops, not negative. 1.103. So that reaction, which, by the way, is the exact reaction that these pennies have, right? If these pennies were 100% zinc wrapped in 100% copper, then each time that we build these things up, we're getting up to 1.1 volts, right? Now, again, this is as it's written on paper, and just like with free energy, there's the as it's written on paper, and then the experimental part that's going to change it. But yeah, roughly each one of these pennies could give us a volt. So if you stacked 9 of them up, you'd have a 9-volt battery, right? You'd have 9 volts. Now, that doesn't mean it has the same total capacitance as a regular 9-volt battery, right? We're going to talk about that a little bit later. So I think we're about out of time. So let me answer a few questions real quick. Any questions? Yeah. Per 1 mole. As this is written, it's written per 1 mole. Other questions? Yeah, Isaac? Let's talk about that next time. Okay, we'll pick up here next time.